This is an application of an artificial neural network that is solved in the GEKKO Python language. We're going to approximate this function y equals sine of x. So just a very simple function sine, and we'll sample it at a number of data points here along the way, and then we'll give that to an artificial neural network and see if we can reconstruct that function. So the very first way that we're going to do this will actually be the second way down here. We're going to have our input x. We'll have a first layer that's just going to be a linear layer with 2 nodes, and then a second layer that's going to have 3 nodes, and that's going to be our hyperbolic tangent activation function as is shown here. And then we're going to have our third layer, which is going to be 2 nodes, and that's just going to be a linear layer, and then our output is going to be the summation of layer 3. Now, one of the ways I like to visualize these is through this nice link provided by TensorFlow, where you can do classification or regression. In this case, we're going to be doing regression for this example problem. So let's just emulate what we have in our network with 2 neurons for the first hidden layer, 3 neurons for the second hidden layer, and then 2 neurons for the third. Okay, so we have our activation function, which is the hyperbolic tangent, and we'll be using that for all layers here, but in ours we're going to have linear input and linear output layer. Okay, so if you just select train on this, you'll see that here's the reward function or the loss function. Okay, so there's our training right there. As it gets lower, it means it's a better fit. Okay, you can also select the different data set here, a little bit more complex, and then click run again, and you'll see it start to train as the blue values are positive and the red values are negative. So it just shows a two-dimensional contour there of how well it's fitting the data points. And then you can also highlight the different neurons and see how those are contributing to the final fit. Okay, so if you just mouse over those, you can deselect this first input, okay, as well, and just go with a single input and see if you can get better training. Or you can add additional inputs as well and see if those inputs help with predictions of the output. Okay, there's other things like learning rate, how fast you converge. There's other regularization rates that you can use as well to try to fit some of the data. Now you'll notice that how far you let it train, that's going to you can overfit some of these models. They're very highly parameterized, and so we want to avoid overfitting. Okay, so that is the neural network playground. I'm going to come back to our example problem here, and we'll go ahead and set this up. We'll also do another example here where we're going to fit it with instead of an activation function that's a hyperbolic tangent, we'll use a cosine activation function. So if we know something about the problem, such as this is, instead of hyperbolic tangent form, there's some structure to the problem, you can input that into one of the different layers, and then when you fit it, you might be able to extrapolate just a little bit better. Okay, and if you just want to see the solutions to these, here's the the sine data that we gave it. Each of those blue points is the cosine, and each of the blue points there, and you can see that the the hyperbolic tangent form is going to, it's not going to extrapolate very well. I think everybody knows this about neural networks. If you don't have the training data set, then it's not going to extrapolate very well. Okay, but inside this region does a very good job of fitting that, especially if you don't have any knowledge about the structure of the input to output relationships. This might be the best method right here. Okay, so let's jump into the code. I'm just going to go through this in just kind of line by line. If you'd like to just get the code and run it, you can do that. There is a I'll just show you where to go to grab that. If you just go to APMonitor.com and then documentation, and then down on the right you'll see GEKKO Python, and there are a number of examples, 18 in fact, to go through. This is going to be number 7 of those 18. We just went through some regression exercises, and there are the exercises in this top link. You can see the list of 18 right there. We're going to be doing number 7 right here. So if you just scroll down, you can open up this notebook and follow along if you'd like. Okay, so there's also the link to the online neural network demo with TensorFlow if you'd like to select that. Okay, let's go and get started on the code. I'm just going to go through and let's go ahead and just do line by line. We'll go ahead and first of all import GEKKO. We'll import NumPy and Matplotlib. And then we're going to generate some training data. And also the here's our x value right here. I'm just going between 0 and 2 pi, and we'll have 20 data points. And there is my y value. So there's my training data set. Then we're going to have our hyperbolic tangent function. Okay, here is the number of inputs. First hidden layer, second hidden layer, that's going to be our nonlinear hyperbolic tangent functions, and then a third linear layer, and then our one output. So we have one input, one output. Then we also have our cosine function. We'll do that in a little bit. I just had those commented out. First of all, we want to initialize GEKKO. We're going to have a training data set and also a testing data set. And so we're going to create our models that are going to include the training and the testing sets. Okay, so for M in model, we're just going to cycle through these. Cycle through this loop twice. So here's our input. We're going to have the x value be our input. We have our layer 1 now. This is our linear layer. We're going to create an array, and these are going to be FV values, meaning that we have the same value for all of the data points. And the dimension of that is going to be n in, so 1 by, and then n1 is going to be 2. Here is our, let me expand this just a little bit. Okay, we have our first layer. This is our first equation. We have basically our input times our weighting 1, and that's going to be our first layer. Okay, we have our next layer. That's going to be, I have 2 parameters for these. Let me come back here just to show the parameters. Okay, we have our parameter for 2, which is going to be the L2. So this is our second layer. We have 2 weighting functions right here, which is going to be weight 2a and weight 2b. And so if I come back over here, I have both of those parameters. Those are going to be n1, that's our hidden layer dimension, which is 2 by 3. So we have a matrix of 6 values for each of those. Okay, so now we're going to be able to select between, if we want our hyperbolic tangent function or the cosine function. So here's our cosine function. And so you just need those 2 lines right there with the cosine, and then we have W2A and W2B in there. Okay, W2B is multiplied by the layer 1. And if we have our hyperbolic tangent, we're just going to replace that with the cosine with the tan H. Same form though. Here's our layer 3 for our network. Very similar to layer 1, it's just a linear layer that maps the layer 2 outputs to layer 3. Okay, and then here's our output. We're just going to sum up the layer 3. Okay, I'm going to flatten the matrices just so we can deal with them a little bit better than in matrix form. So just making a list out of those matrices. And then the next part is we're going to fit the parameter weights. So let's go through and select our training model. and then the value is going to be equal to x. So those are the lin space values between 0 and 2 pi, the 20 data points. Okay, and there's the output function, y. And then I need to say that we're going to use those measurements. I'm going to turn on the feedback status for that y value. And then for all of the parameters in layer 1, I need to say that we want to use those measurements as well. We're going to give them some initial guesses. And turn the status on. So status meaning that we're going to let the optimizer try to decide the value, but we have a f status and mes value, a measured value, just to be able to give them initial guesses. Okay, same thing for layer 2. We just have the status on for both of those. We'll turn the feedback status on as well, so we can give them measured values. So if you have any initial parameters that you'd like to put in there, you can do that with the mes value. And here's our layer 3, very similar to layer 1 and layer 2. iMode 2, that is the mode of operation. Okay, so this is this parameter regression mode for GEKKO. And then we have solver 3, that's going to be the IPOpt solver. EV type 2, that is going to be a squared error objective. So our output, we have a model minus measured value, and then we'll square it. And then we'll solve it. So this is going to do the fitting of the neural network. And then we want to be able to go into a testing phase. So test it, the sample points, not just inside the training set, but also outside it as well. Okay, and so we have our, we're going to transfer the the new value from the fit, okay, from the training over to the testing. Okay, and then you can see the feedback status is 1, and we're just going to transfer those over. We'll print out the weight 1 as well, just to be able to see what the value is. Here's our weight 2 as well. We're going to transfer over the new values into the measured for the testing and turn on its feedback status, so we use those measurements. Okay, and then print those out. Here is the weight 3. Okay, and then we say here's our testing values. We want to go between -2 pi and 4 pi with 100 data points, so that's for our testing. And again, it's going to be iMode 2. Solver 3, which is IPOpt, and then solve it. Okay, the next is just going to be plotting all of these. So let's just go ahead and create the plots. Okay, and let me come back here. Okay, so there is our plot, and we have these, we're testing it, we had the test and also the measured values there. Okay, so when we run this, let's just go ahead and I'll open this up. You can do it either in the Jupyter Notebook, or you can do it through any other environment that can run Python. And I'll just run this with the IDLE editor. And here is the cosine one. Let's go back in and change this to be instead of the cosine. Okay, we're going to use the hyperbolic tangent. So let me just go ahead and edit out, comment out this region. We'll just use the hyperbolic tangent. Okay, run it again, and those were the parameters that it came up with for the different layers. And so let's do this with, this is going to be our hyperbolic tangent. There are all the parameters, many more parameters, and there you can see the fit to that data. Okay, so this is the how to do the neural network. We're going to be developing some additional functionality to simplify some of this. This seems like a lot of code to be able to do the different layers, and especially where it's pretty standard like this. We're going to be developing some functions, so check back later. It should be a little bit easier, simplify some of the coding for these neural network models. Okay, I hope you enjoyed this tutorial. This is just a simple sine function. One of the main takeaways from this is that, depending on the structure of your model, you can have many fewer unknown parameters. So in this case, we only had, just a handful, just 4 parameters that we were fitting. And in this case, we had many more, parameters. Both are working well. If you have some knowledge of your system, you can often enforce that in one of the layers, or add things like constraints or other features of the fitting that give the fit more information. So this approach in GEKKO is also very unique. It doesn't solve the problem like TensorFlow or some of the other packages. It actually takes these equations and sets them up in as a nonlinear programming problem and solves it with exact first and second derivatives with a gradient-based optimization approach. And so this one probably isn't the best approach for extremely large data sets. TensorFlow and others, they just use a steepest descent method with a basically an explicit solution to each iteration. You can't necessarily have constraints, hard constraints in those iterations. So it's solving it in a different way than a lot of the other neural network packages that are available out there. We're going to continue to develop this, especially for hybrid, what we call hybrid modeling, where you have some knowledge of the structure. This would be an example of where we would use hybrid modeling. Maybe we have things like material or energy balances that we can enforce on the problem so that we can extrapolate better outside of the training data set.